well, welcome everybody. This is day 2. We have lots of talks today, just like yesterday, lots of very exciting talks. And this morning, to kick us off, we have Xinliang An from Singapore, National University of Singapore, who will be talking about anisotropic dynamical horizon arising in gravitational collapse. I'm very much looking forward to this talk. So Xinliang, please.
Yeah, first I want to thank Martin and all the other organizers for the invitation. It's a great pleasure to be here. So yeah, I will talk about the anisotropic dynamical horizon arising in gravitational collapse. So this talk is based on joint works with Dejan, Gajic, Qing Han, and Ruixiang, Zhang. And yeah, we will talk about Einstein equations in R3+1. In particular, below we will focus on two model equations. So one is the Einstein real scalar field system. The other is the Einstein vacuum equations. And right, so below it's a Penrose diagram for the Schwarzschild solution to Einstein vacuum equations, and this is the trapped region. So each of the points stand for a two sphere, which is a trapped surface, and this is a two sphere, which is not a trapped surface. So let's say draw the picture for the trapped surface, and once it is a trapped surface, it will be of the following shape, which is based on S2. We can define the non-expansions. We have the outgoing and incoming direction. If both the non-expansions would be negative, then this point-wise, then this is called a trapped surface. And so this is a standard two-surface in Minkowski spacetime. Clearly, we can see that one of the non-expansion is positive, one is non-expansion is negative. So yeah, this is the difference. And the area of the trapped surface will increase no matter along which direction, which within the light cone. So in below, let's first discuss some results on trapped surface formation, and we will work on double non-foliation. So yeah, the first thing is we're starting from the really easiest one, which is Einstein-scalar field system under spherical symmetry. So for the metric of the 3+1 dimensional spacetime under spherical symmetry, so we adapt the following double non-ansatz. And so with these ansatz, we can rewrite the Einstein-scalar field system into the following system for R, for omega, and for the scalar field. Okay, and these are the equation system. And I want to mention there are some very important and interesting coupling structures here. They are very useful. And right, and so each point here corresponding to a two surface. Yeah, we use double non-foliation. This will be the constant u direction. This will be the constant v direction. Okay, each point here we can define the Hawking mass, which is defined here according to the metric. And right, so yeah, for the initial data here we prescribe two dimensionless quantity, and they are very useful to consider the dynamics. So one is we consider the we define the eta. Eta is defined to be the difference of the Hawking mass divided by the radius here. And then, yeah, intuitively, this tells us how much, in the average, how much mass actually sent out from the incoming direction. And we also define another dimensionless quantity, which is called delta. Delta, which roughly tells us the change of the geometric shape. It is the difference of this radius over this radius, and this is defined here. Both eta and delta naught are dimensionless quantity. We can compare them. And so let's recall a classic result by Christodoulou in early 1990s. So he defined a function which is of the following form as E. So he proved the following. So try to solve the Einstein scalar field system under spherical symmetry. So we prescribe characteristic initial data, and this would be the U equal to U naught. This is V is equal to V1. And if for the initial input here, and if the eta naught is larger than the E naught, E is the function which are defined, then in the shadowed region, there will be a trapped surface formed with both partial VR and partial UR to be negative. So when delta is quite small, which is when this delta is quite small, so the leading terms for this function would be delta log 1 over delta 1 over delta. So yeah, so because the comparison here is if eta naught is larger than delta log 1 over delta, then a trapped surface is formed. Because both of these actually are the dimensionless quantity. So we call it, because of this delta loss, so we call this to be an almost scale critical result. This is by Christodoulou. And once a trap surface is formed, so for Einstein-scalar field system under spherical symmetry, Christodoulou further proves that the generic Penrose diagram for this system, which would be of the following picture. So here is H is the event horizon, and this would be the apparent horizon. We have the trapped region, and there will be the space-like singularity, and yeah, this will be the time-like infinity. So Christodoulou, in one of his paper, he further showed that in the exterior region here, and for this picture, so eventually the metric in the exterior region will settle down to a Schwarzschild metric, which is there is some final boundary mass M, right? Okay, so what we can, let's say based on this picture, what would be the next step question to ask? So there is a natural question, which is how strong are the space-like singularities? So Christodoulou considered part of this question in his paper. So he employed the ODE type estimate and obtained the lower bound for the Quatermain scalar. And via some algebraic calculation, he showed that the lower bound for the Quatermain scalar will be 1/r to the power of 6. And here, for the numerator, there will be the Hawking mass square. But in the trapped region, we know that the Hawking mass will monotonely increasing. So this is always bounded by a non-zero constant. So Christodoulou really showed that the lower bound is at least 6. So what would be the upper bound for all the geometric quantities, in particular for the Quatermain scalar? So this is an interesting question. And the following qualitative extension principle by Christodoulou in other papers, it can be proved that for the Quatermain scalar, when it is very close to the space-like singularity, there will be the double exponential upper bound. So yeah, this will be exponential 1/r. And because the lower bound would be a polynomial, which is 1/r to the power of 6, we really want to know if it's sharp. Can we improve this to the sharp scenario? So, but to get a better upper bound, we need to give a totally different proof, which means we need to improve all the estimates into the quantitative sharp estimates. Right. So in a work with Ruixiang Zhang in 2019, so for the Einstein-scalar field system under spherical symmetry, and with the same initial data Christodoulou used, and we can show that no matter for in this picture, no matter for which point along the space-like singularity, so the Quatermain scalar, there is always an upper bound, which is a polynomial upper bound, which is there exists n depend on the initial data and the location, such that the upper bound would be 1/r to the power of n. And our proof and the result is non-perturbative. And this would be true for each of the points along the space-like singularity. And and because we have the lower bound by Christodoulou, which is 1/power of 6, so the polynomial rate would be sharp. But in order to doing so, we need to prove a really key step is to prove that for the scalar field. So we want to prove that for the blow-up rate for the scalar field close to the space-like singularity would be exactly 1/r to the power of 2. So we cannot lose anything. So if we lost an epsilon here, so we can only prove exponential blow-up rate. There is no the polynomial, and this 2 would be we have to make sure this is 2, and the constant this n will depend on the constant d1 tilde and d2 tilde. In principle, this is quite hard to calculate because So the blow-up rate 2 for the scalar field here is sharp, and this implies that for the scalar field itself, it will be the blow-up rate will be log 1/r. This is consistent with a result by Christodoulou and Zbierski. They studied the linear wave equation in the Schwarzschild metric, and they derived the asymptotics for phi, and this is the leading term. And so n will depend on d1 tilde and d2 tilde. So is it possible that we can calculate this n for some scenario? And this would be the next result, right? This how about this n? Can we see something more explicit? So in a joint work with Gajic 1 year later, so we really can calculate this n, but when it is close to the time-like infinity. So we connect this to the Price law, and with Price law, we really can calculate what this n is, and this is the result. So so we consider the region which is closer to timelike infinity, and this is still the spacelike singularity. So we prescribe initial data along the event horizon, which is consistent with the price law, and also we prescribe data along the H bar. And so when it is quite close to the timelike infinity, we can show that the Blob rate, both upper bound and the lower bound for the Gajic scalar. And it is very interesting. The Blob rate would be 6 Christodoulou's lower bound plus positive corrections. And the correction, both of the corrections will go to 0 at the point moving towards the timelike infinity. So here, so in this picture, along this direction, the wave will go to infinity. So this term eventually will go to 0. And both rho and the sigma and the d1 would be positive constants. So here is the rho will depend on our method, depend on only the final bounding mass here. And the sigma will depend on the initial data, also depend on here. And what is this D1? This D1 is related to the price law, because along the event horizon, we prescribe initial data, which is related to the price law, which is these terms we have the leading behavior and with the sun. So here is the both D1 and D2 to be positive, and the P and the Q satisfy the following assumption. So so the bubble result link the curvature Blob rate to the price law along the event horizon. So so since our sigma, rho, sigma, and D1 are both positive, so the Blob rate here actually is strictly larger than 6. This is a little bit surprising to us when we just found it, because in the beginning we thought 6 would be sharp, but this is indeed strictly larger than 6. But when the wave goes to timelike infinity, this rate goes to 0, so which is still converge to the Schwarzschild scenario. And the Blob rate will converge to 6. And also, if we change the location, the Blob rate along B is not limited to discrete choice of it's not limited to discrete finite choices. And this is a new Blob phenomena. So so this So this is the first result of this type on spacelike singularities. So before the work by Mihalis and Davomos and Luke and O and there are many other authors, they link the price law along the event horizon to the weak non-singularity. So where the radius is still has a lower bound. But here we related the price law to the really strong spacelike singularity. And moreover, we also derive the mass inflation here, and also derive the converging rate of the metric to the Schwarzschild metric here. Right. This is the work with Gajic. So okay. So the next question is this is what we just said for the spherical symmetry. So what we can see about the below picture out of symmetry, it would be really hard. But right. So in R3+1 for Einstein vacuum equations with no symmetry assumption. So what could happen? This is really something we hope to know. And is the following picture still true? So we don't know at this moment, but my previous works in this direction address the region close to S0 along the apparent horizon. Yeah, which is along in this region, we have a relatively good understanding about what's happening. So the story will date back to a breakthrough result by Christodoulou in 2008. So so this is the no symmetry at all. So we still there's no symmetry at all. We still are working with a double non-foliation, and we will have the E4 direction. So each point corresponding to a two sphere. Along the E4 direction, we can define the non-second fundamental form along the E4 direction, which is the K-B, and we also can define the traceless part, which is K hat. So the Christodoulou result is, so he solved the Einstein vacuum equation in this yellowed region, and he prescribed the data, which is trivial data here, and he prescribed a short pulse data, which is the K hat. There will be both upper and lower bound, which is, he introduced a small length, which is delta. And it will be delta minus a half over U. So U infinity could be very far away from past non-infinity. So and under this initial data, he can show that a travel surface of radius 1 will be formed. And so in his proof, he used both the upper and the lower bound for for chi. And also the really key part is to show the global existence for Einstein vacuum equation. This is a large data problem in this quite a large region. Okay, so yeah. So Einstein vacuum equations are PDE system coupled by many tensorial quantities. So Christodoulou gave a detailed control of all the terms with the volume. And later, so by Sergio and Kahneman and Rodiansky's work, and later I extended their approach. So we give a simplified proof with a more systematical approach to prove his main result. And in Sergio and in Kahneman and Rodiansky's paper, they define a signature as one, which is related to the delta weight, called the signature for short pulse. And I defined in this paper a signature for decay rates, which is for the U weight. Okay, and several years earlier, so I gave a short proof of trapezoid formation with only using the signature for decay rates, and I proved this in the far field regime, which is which is very far away from the center. But the result here is I proved the scale critical result, and once I scale everything back to, I do a scaling and do a rescaling, I can going back to here, and if I let the A is delta minus 1, I can get Christodoulou's main result. So but this is proof is relatively short. And there's another very important result by Kahneman, Luke, and Rodiansky, and they showed a fully anisotropic trap surface formation mechanism, which is they really relax the lower bound assumption for the initial data. And because for the work here, we need both the upper and the lower bound to be roughly the same, but they can relax the lower bound a lot. Yeah, I will talk about more about this here. So. Okay, and another interesting result, which is by me and Luke in 2014, which is we improve Christodoulous result to the scale critical regime. So which is we introduced parameter A such that the A will be much larger than 1 and less or equal to delta minus 1. And we prove the following result, which is we solve the Einstein vacuum equation in this colored region. And here we we prescribe data at U equal to 1. And the chi-hat would be square root of A, and we also prescribe trivial data here. So what we get is we formed a trapped surface with a very small radius. So this will be a radius of radius delta. Because we can choose A to be a universal large constant. This is really a really tiny trapped surface. And then, so here is the shared tensor will be square root of A over U. And if we let A to be delta minus 1, we recover Christodoulou's main result. And the benefit is we can let A to be log 1 over delta, which is consistent with the first result we mentioned for the almost scale critical trap surface formation criterion. And then we can let A to be log 1 over delta. The sharp case is we let A to be a large universal constant as 1,000. And unlook is the first scale critical result for Einstein vacuum equations. So 2 or 3 years later, I realized this result can be used to do the following, which is, because what we proved with Luke is a scale critical result. So, which is along the initial data here, each of the points. So the initial data is only dependent on A, does not depend on delta. And via a scale critical argument, not only we proved existence in this orange region, I can also further extend the existence to the whole colored region. So now I may have a chance to show that the whole apparent horizon or somehow the black hole, which is emerging from the center. And this is what I want to do in 2017. So which is And the boundary of the black hole region is also further solved. So the dashed line here within this colored region is a boundary of the trapped region, which is apparent horizon. And each of the dots corresponding to a marginally altered trapped surface called a modes. So the way we find this modes here is we giving each incoming non-cone. So we find a unique modes along the non-cone, and then we put all these modes together. I can show that this will give us a smooth apparent horizon, except at the first spacetime singular point. So this approach to get the modes is different from the approach by Lars and also on Eshma and Metzger et al. So they solve the modes. They have very famous papers which try to solve the modes along spacelike hypersurface via Zhang's equation. So here is we solve different elliptic equation because we solve the modes along incoming non-cone. So yeah, it's quite different. So more comparison will be discussed in later slides. So yeah, so okay, so what is a question here? So which is giving each incoming non-cone, and we try to find the modes which is along the non-cone. We call it right. Okay, so in order to find the modes, so this is a kind of a free boundary problem, which is we so we let this unknown modes to have the coordinate. Yeah, because this is u bar is fixed, so we put u bar here, but we let u will depend on r. So r will be an unknown function, depend on both the u bar fixed and the angular variable, which is omega. So yeah, this is an unknown function we want to solve. So based on this two surface, we recalculate what would be the corresponding trig chi prime and trig chi bar prime. And to get the modes, we really need this to be 0. And this to be negative, this is never a problem, so we don't worry about it. So right, so the equation for the modes will be translated to a elliptic equation. So which is the trig chi prime is equal to 0. We will translate it to the following quadrilinear elliptic equation for R. So this is quadrilinear because the metric of the induced metric will depend on the location. But interestingly, the difference between Zhang's equation is so the metric only depends on R, does not depend on the gradient of R. And right, there is some important nonlinear structures. And there is M. M is somehow interesting. So intuitively, M tells us along each angle, so what would be the mass we shoot in. And so in the short pulse regime, and so this is always be the u bar times a, and with a constant, the constant will be between 0 and 2. So this u bar a is coming from integration from 0 to u bar, and the k-hat square, yeah, we can put a u square, and this is related to here, and yeah, this will be a constant, right? Okay, so yeah, I want to solve this elliptic equation, and so the first paper I wrote in 2017, which is I can solve this elliptic equation for the scenarios and not very far away from the isotropic scenario, which is the most isotropic scenario will be f is equal to 1. So, but there is allowed f to be between 20/22 and 20/21 and 22/21. So this is not epsilon close, but it is somehow not far away from 1. And yeah, so to solve this elliptic equation, I employed a priori estimate, which is from C0 estimate, C1 alpha, and C2 alpha. And then I employed a method of continuity to solve this nonlinear elliptic equation. So yeah, this is more like a geometric analysis paper. And really the key is the gradient estimate. And here I try to use the Bochner formula to doing so. But immediately I get a difficulty, which is let's say if I do not construct this kind of H, if I just directly use the standard Bochner formula, and there will be a term which is gradient R to the power 4 and gradient of R to the power 2. But the sign in front of here will be a negative sign. And if I have a negative sign, I don't have the good maximal principle. I can prove nothing. So yeah, it really takes me some time, and I construct the following function, which is HR. So R is a unknown function here. And if I put the HR here, not only I can make sure that the sign in front of gradient R to the power 4 is positive, I also can make sure that the sign in front of gradient R squared is also positive. So yeah, to make this positive, it's really quite hard. So actually after some trying, because right, this is kind of compared with this term, this will be the low order, right? And the rest would be a very small term. And using maximal principle, not only I can prove that the gradient R will be bounded, I can further show that gradient R will be less than 1. And this will be very important to describe some property about the apparent horizon. Okay, so right, so the result there is I solved the Einstein vacuum equation with the following initial data, which is in the short pulse regime, we put Minkowski data here, and we set the k-hat to be outside square root of A, and then we do the integration here. And intuitively, this will be like the u bar times A, but we have the coefficient. So here I require the coefficient to be between these two numbers. So along each incoming non-cone, and I can show that there would exist a unique modes. And and if I put all these modes together, except at this center, and this will be a singularity. And then the other part of the apparent horizon would be a smooth apparent horizon. And right, our next result, which with Qing Han, we will generalize this result to the quite a general anisotropic scenario in the short pulse regime. And we also will show that the corresponding apparent horizon, even for the anisotropic scenario, would be spacelike. So yeah, sorry. Okay. So the questions. Sorry. Yeah. Okay. Then I move on. So yeah. So 2 years. 2 years ago, so with Qing Han, we proved the following result. So yeah, so which is we still try to solve Einstein vacuum equation in this colored region, and we prescribe Minkowski data here. And for the incoming data, so we relax, which is approximate square root of a. We can let this to be less or equal to square root of a, which this chi-hat could be 0 for loss of positions. Okay, so which is we will have the condition which is we required, which is this will be f times u bar of a. Yeah, we know this will be of the order u bar times a, but the coefficient is not known. So here we allow the f to be between 0 and 1. So especially when this is close to 0, not close to 0, but we can allow this to be 0 for many of the parts of the S2. So the only requirement is we require this f to be positive within some very tiny ball, which is because we prescribe smooth initial data. This is really we let m to be positive at certain points, right? So we will have the lower bound mi and the point pi and the ball, the component of the ball, which is epsilon I. So I will mention these 3 parameters later in the later slides. Okay, so right, and then so for here we can still show that along each incoming non-cone there exists a unique modes and under very general, yeah, and also for the general short pulse initial data conditions, and these modes will form a smooth and space-like hypersurface. So yeah, this is also so-called the dynamical horizon in the physics literature. So yeah, I want to mention that the condition f between 0 and 2 here, this is the most general allowed initial data we can prescribe in the short pulse regime, because we really need this is less or equal to square root of a to control the hyperbolic part, right? Okay, so yeah, there is a folklore belief related to this, and this is related to Professor Galloway's writing. So in 2005, so Ashtaka and Galloway, they wrote the following, which is there is a general expectation that under the favorable circumstances, so a marginally trapped tube, this is apparent horizon, that forms during a gravitational collapse become space-like. That is a dynamical horizon soon after collapse. So yeah, so the result by An Han actually confirmed this folklore expectation in the short pulse regime with a general both isotropic and anisotropic initial data. Yeah, but we confirmed this in the short pulse regime. So yeah, and also this result, what I just mentioned, it also provides the evidence which is related to a local version of weak cosmic censorship, which is under the initial data assumption prescribed as above in our theorem. And there is no even locally naked singularity form close to the center. The reason is in this picture, we can show that this is the first spacetime singularity. And immediately from this point, there will be a space-like apparent horizon to censor it. So there's no way for even local observers outside of the apparent horizon to see this point. So right, so this is also related to yeah, it's of this provide evidence for the following. So right, and yeah, so the analytic method we used here for in this new paper would be quite different from my previous result. So here is we use extensively the hyperbolic the estimates, which is, and also we use the non-perturbative elliptic techniques. So in my previous paper in 2017, so still somehow the way we get the C1 estimate, and it's still kind of in the perturbative regime, but here is not right. So the really difficult the step is to go through the details of Moser's iteration, which is from C0 to C0 alpha, and go through the detail to see how this is depend on each of the parameter. And then we boost the regularity from C0 alpha to C1 a third to C2 a third. So so there is, we didn't derive the C1 because you can imagine it is not possible to, almost impossible to design an H like what I designed here for make this argument work, because this is really the anisotropic scenario. And we use totally different elliptic method to doing so. And also, and also in the proof, we need to use we need to show the invertibility of the linearized the operator. We have to prove that the positivity of the first eigenvalue for quadrilinear problem. And we also crucially need to use the strong maximal principle. So we also get the regularity estimate about the modes, and also the spacelikeness of the apparent horizon are proved via the elliptic estimates. And so so remember, so we said there will be a constant mi and epsilon and p and pi, which is related to the initial data. We can trace all the constant in the estimate, and it is also related to the shape in the next slides. So besides this result we proved, so we also gave the first mathematical examples of anisotropic modes and anisotropic apparent horizon that formed in dynamics. So we really prescribed the data from the non-trapped characteristic initial data. And so the shape of the modes formed, which is they will have the single or multi values. So the picture above demonstrates, especially this two surfaces, demonstrate a finger-shaped modes, which is with two values. The two values is because we have these two really the lower points compared with the point here. So, and also via our approach, the dynamically formed not only two but multi-varied shape of modes is explicitly determined by the mi, pi, and rho I prescribed in the initial data, which is the lower bound and the support of the ball and the location of the ball, and the shape of the modes is explicitly related to here. And right, so okay, so so to achieve this, and the way we do it is this is the mode we want to solve, and we construct very explicit upper barrier and the lower barrier to somehow to make sure the shape of the mode is of the following. And so for the upper barrier, so we generalize the result by Klein-Mann-Luke and Ruixiang. So so and we generalize their construction and provide the description of multi-values, right? And also to get the lower barrier actually something interesting. So our construction for the anisotropic lower barrier actually is new, and by our proof we can show that a unique modes exists along the h bar u bar, and it is bounded by these two barriers. So I want to mention that the uniqueness is not only in this region. The uniqueness is almost for all the region I can control for the hyperbolic part. So so which means we can so this is these two barriers I try to control the shape of the modes to make it really anisotropic. But if we don't care about the shape, so we can construct a mode which is quite inside and on-trapped surface, and we can a trapped surface quite inside and on-trapped surface which is outside, and then we have the uniqueness in between. So right, so because we can control the barrier, the anisotropicity of the modes can thus be calculated. We are calculating, because we have the barrier, so we can calculating the corresponding the upper bar and lower bar at these points. And by doing this, we can really demonstrate this is anisotropic modes. And all these things are explicit from the initial data, which is there's no trapped surface at all, right? Okay, so right, once the apparent horizon is spacelike, which is guaranteed by the result with Qing Han. So the following theorem holds, which is along the apparent horizon, the area of the modes actually will increase when the u bar is larger, and the area of the modes will shrinking to 0. So this research actually along this direction was inspired by Ashitaka and Krishna's work back to 2003. And there they give the definition of dynamical horizon in physics literature, and they assume that a dynamic horizon exists. They established black hole thermodynamics on it. So with no symmetry assumption, the above results, which is us, are the first showing that both isotropic and anisotropic dynamical horizons can really form in dynamics. And if we consider this theorem with regard to the area as the entropy, this is really corresponding to the second law of black hole thermodynamics over there, right? So I want to compare so I want to compare this approach with the very famous the approach by Lars Eschmar and Metzger. Since Lars is here, I really hope to hear his suggestion and the comments after the talk. So so Lars and et al.'s work inspired our exploration. So for in their approach, they try to solve the modes in a different setting, which is giving a space-like hypersurface. And once you have a trapped surface inside, there is untrapped surface outside, and there will be a mode in between. So which is they solve the modes on space-like hypersurface with a trapped surface and an untrapped surface given in the assumption. And but their proof holds for the very broad setting. So for our result here, it's only for the short pulse regime, but we deal with the most general data allowed for the short pulse regime. And so here we prove the formation of the dynamical apparent horizon arising from the general, both isotropic and anisotropic untrapped characteristic short pulse initial data, in this short pulse regime. And so for and here to study the gravitational collapse in the short pulse regime. So here we use a different approach. We are solving a different elliptic equation, and we prove the quantitative estimates about the modes. We have all this a priori regularity estimate for the modes, and we also have the we have the uniqueness here. So okay, let's see. And the next slide. So here we solved the modes along so here for us, our approach, we solve the modes along an incoming non-hypersurface, and the elliptic equations used here is completely different. So we use a new quadrilinear elliptic equation, and its solution remains smooth at the location of modes, and we derive all the a priori estimates from scratch, and even to including the anisotropic scenario, and obtain the quantitative estimate and information. So for in their setting, it's quite general. They use the Zhang's equation. So Zhang's equation blow up at the point corresponding to modes and some other points. The outer boundary of these blow up points are corresponding to the modes. So the a priori regularity estimate and the unconditional uniqueness via Zhang's equation actually are quite hard to get. And this new approach in the short pulse regime, we obtain this information. And also, Lars also introduced the so-called strict stable condition to study the property of apparent horizon in their setting. But here, this condition cannot be directly verified using only the untrapped characteristic initial data, especially for the anisotropic scenario. And so with this new approach in the short pulse regime, we also construct explicit finger type, the single and multi-valley anisotropic apparent horizons arising from the characteristic initial data. So this very explicit construction from the initial data actually are new. So we also prove that the apparent horizon in this setting emerge from only one singular spacetime point, and we can do this because this is related, and we also use the scale critical hyperbolic techniques to demonstrate this, which is so remember, so this is the region which is we use the scale critical result, and we can get it. So and this will be the first spacelike singularity. So as we really use the really sharp the hyperbolic part to doing so, and when we're doing this, we use double non-foliation. And the spacetime region we can solve will be up to the first singular point along certain angle. So when we solve this from the hyperbolic part, we use double non-foliation. So in this setting, to solve the modes along the incoming non-cone will be both natural and necessary. So natural, because we use double non-foliation. Necessary is so because we can only control the spacetime region along certain angle, starting from this one is very close to O because we want to approach in O, right? So so we cannot probably even construct a suitable space-like slice to operate their research. So so we we need in order to consider the region close to O, we really need a different approach, which is here. So right. So so hope that in the next conference I can present some further results on gravitational collapse with or without spherical symmetry. So I still have I still have maybe 15 minutes, so I can talk a little bit more. So for the rest of this talk, I hope to report some explorations on fluid dynamics. So the reason I want to do it here is I really want to say that the my experience about my learning about the mathematical GR really motivated me to think about some problems in the fluid side, and later we will see some connection. So let me first briefly mention the two results, and then I will go back to the first one, talk about some details. So joint with Dr. Chen Haoyang and Dr. Anisotropic, so we show that we prove the low regularity idioposness for elastic wave for compressible Euler equations and for compressible ideal MHD system in R3+1. So we generalize the Lindebrand's classic idioposness example for the single quadratic linear wave equation to the physical systems. And later I hope we can use roughly 5 minutes to talk about some details. And then this will be the compressible fluid. And then the next result I want to mention is with Mr. He Taoran, is still a PhD student here, and with Dr. Li Te, a postdoc here. So we proved for the incompressible Navier-Stokes equation, we proved the nonlinear asymptotic stability of the 2D Taylor-White flow. So the Taylor-White flow would be a circular flow for the 2D incompressible Navier-Stokes equations, and so which is the flow will be which is in the annulus region. This will be the flow. So so we use the resultant estimate and pseudo spectrum bond, and really to show that we have the nonlinear asymptotic stability of this flow. And so I don't have time to talk about this result, but I hope that maybe sometimes in future I can talk more about this direction. This is with the incompressible scenario. So I may use roughly 5 to 10 minutes talk more about the compressible result, which is more related to the in terms of the techniques, it's more related to here. So so the results with Chen and Yin. So we studied the physical quadilinear hyperbolic systems with multiple wave speed. So in particular, we consider two types. One is the elastic wave equation, which is a system, which the U would be a vector. This is the vector value functions, and we will have the C1 and C2. C1 is larger than C2, and right, this is the system. This is quite important system for the elasticity. And we also have the 3D ideal compressible MHD. So if we let H to be 0, we will go back to the 3D compressible Euler equation. This will be the compressible Euler equation coupled with the Maxwell equation, and here. So our equations are the following. So for the 3D elastic wave equation, we prove the idioposness for the H3 cross H2 initial data in the following sense. So we construct a family of compact support smooth initial data, which is in the H3 and the H2 norm. We have a family of the initial data. So as eta go to 0, the sum of the initial data will go to 0, but each of the initial data is associated with the shock formation phenomena, and the shock formation time as eta go to 0 will also go to 0. So there will be instantaneously shock formation, and we moreover show that not only the shock formation, we can also prove that the H2 norm of the solution will instantaneously blow up. So this is for the elastic wave. And so the above results generalize the Lindebrand's sharp H3 idioposnes for single wave equation to the wave system with multiple wave speed. And we hope that this H3 idioposnes actually would be sharp. And if we rewrite the elastic wave equation using Lagrangian coordinate, so we can have the Eulerian coordinate. So our H3 idioposnes in Eulerian coordinate will translate it to the H2 idioposnes, and this is consistent with our next result. So our next result is for the 3D ideal compressible MHD. So we show that, so we also have the desired idioposnes in H2 in the same flavor, which is we design a family of initial data, and as eta go to 0, the data go to 0, and we will have instantaneously shock formation, and there will be blow up of each one norm. So I think what is interesting is not the result, but the way we found to see the phenomena. So the difficulty is coming from we will have the multiple traveling wave speed, and for the MHD there will be there will be 7 characteristic strips, they can travel in all different directions. And in particular, there will be two strips, and their traveling speed will be almost the same. Will be almost the same, which means there will be some waves. They can nonlinear interact with each other for a long time, right? And so what we want to show is we consider the spacetime regions, this decomposition really carefully. So we start the regions in each of the strips. And we union R3 and R2, R5, and Phi6. And we consider the darker green region, the lighter green region, and the early, which is everything is overlapped together. So the result is we show that for the R1, okay, and one of the quadratic strip, and the first shock will form in R1. And before the first shock, and for all other places, there's no shock at all. This will be the first shock. And this is what we can show for here. So in particular, if we let H to be 0, so our result will be reduced to the 3D compressible Euler equations, which is of the following form. We allow the non-trivial entropy here. So so our result thus implies the following H2 hypothesis for Cauchy problems of the 3D compressible Euler equations with respect to the fluid velocity and the fluid density. So so our result here is sharp. The reason is the following. So if we look at this picture, so for the 3D Euler equation, we have two physical quantities. One is the velocity, one is the vorticity. So this is the HS corresponding to the regularity for the velocity. This will be the HS prime corresponding to the regularity of the vorticity. So if we consider the classic local hypothesis for 3D Euler equations, in this we know that in this triangle region, we will have the local existence, which is with S larger than 5/2. And recently, there are very good, very interesting and impressive progress made by Qing Han, also disclosed Luo, Ma Zong spec, and later by Zhang and also Lars here. They improved the local hypothesis result, so here we use Qing Wang's result, but they are all related, right? So Qing Wang showed that not only in this triangle region, she also showed that in this very thin grid region, we also have the global existence. We have the local existence, and so there is a conjecture that the local hypothesis will be true in this darker gray region. So, right. So so our hypothesis. Okay. Before that, let me mention. So this solid line, which is corresponding to quite famous hypothesis by Bernoulli, but for the incompressible scenario, which is they consider the hypothesis which is based on the H3 half for the vorticity, which is for this dotted line. So intuitively, Bernoulli's result show that there will be the hypothesis. So our result here with Chen Haoyang and Anisotropic, we really give the whole solid line, which is on the left, which is we really show that this is our hypothesis. So this will be a desired result for 3D Euler equation in terms of the local hypothesis, right? So okay. So I still may have some 2 or 3 minutes. Maybe I can state the result with Dr. Litter and Taoran here. So right. So here we consider the 2D incompressible Euler equation. This is for the incompressible scenario, and this will be the equations